1 and 2, right? That's it? Test 1 and 2.
Yeah, I guess that's it.
Alright. Let me... Does anyone else want to stream, or I'll do it again?
I think you should do it. You did a really good job.
Alright.
Facts.
Alright. One sec. Okay. The first exam. Alright. This is the first one. No, this is the spring, this is the fall. Alright. Start with the fall 2022. The following program is loaded into main memory with offset 16. It will execute on 8-bit architecture. Assume each data memory location contains value 18 and each register has the value 2. Okay. It uses an 8-bit architecture. That means every word is 1 byte long. So instead of incrementing by 4 for every address, you gotta increment by 1. Since 8 bits is 1 byte. So, that being said, maybe...
Wait, hold on. Let me get my thing recording before you begin. Sorry.
Yeah. I copy this or something? No, of course not.
Okay, let's try.
Okay, how am I gonna write on the screen? Hold on. Try to figure this out. Alright, I'm just gonna write 1. This is gonna be like for the instruction 1. 1 is, it says that the offset is 16. Offset is the address of the first instruction, always. And then since each instruction is 1 byte long because of 8-bit architecture, then the next instruction is byte 17, next is 18, 19, 20, 21, 22, 23. And that's it. That's just labeling our addresses for the instructions. And then from that, we answer these questions. Also, sorry if I'm stuttering. It's my first time looking at this test. Provide the value for PC register during the exec stage of instruction 4. Okay, so exec is... instruction 4 is R-type. Why? Because it accepts 2 registers. It's doing some operation on them in the ALU, and it's storing it in R3. R-type right here, uses the fetch, decode, exec, and write backstage. It doesn't go to memory because there's nothing to get from memory. There's no address. Okay, so in this case, they're asking for the value of PC during the exec stage. So PC during the fetch stage, it's set to the address of the next instruction at the end of the fetch stage. So if we're in instruction 4, we just finished the fetch stage, the value of PC is going to increment to the next instruction. And the next instruction's address after instruction 4 is instruction 5, which is 20. So the value of PC during the exec stage is going to be 20. That's the answer for 1.
Oh yeah. If you could send your notes like after the recording, or after the review session for
You
everyone
mean
else
like
to like,
this?
yeah, that.
These?
If it's possible to share it with us,
Yeah, sure.
all right. Bless, bro.
Yeah, no problem. I'm correct on this. Yeah, I'm correct. All right, next. Provide the value for the MAR after the exec stage of instruction 4. Okay, same instruction. I'm just gonna use these because these are very similar. R2 plus R3, whatever. You can change this to minus. It's the same deal, same stages. So then it's asking for the value of the MAR after the exec stage. So what was left in the MAR? Okay, we loaded from PC. That's the last time we loaded into MAR. Since we don't go to memory, we're not loading anything in the exec stage of an R type. So the last time MAR was changed was during the fetch stage of instruction 4. And in that fetch stage, we basically put the PC, which is the address of instruction 4. And the address of instruction 4 is 19. That's the answer. Part B. And then the value for the MDR at the end of the mem stage of instruction 5. Okay. Instruction 5 is a store because you're taking the value from R1, you're storing it into memory at 18, address 18. So let me go here. For store instruction, uses fetch, decode, exec, and map. Now it's asking for the value of the MDR at the end of the mem stage. What happens in the mem stage, it just got back, like it just wrote the data back to the CPU into the MDR. Write data in MDR. Oh, whoops, sorry, this is store. Sorry. The MDR was loaded with what was in R3, or in this case, no, in this case it's R1. MDR was loaded with whatever was in R1, and then it's sent on the bus with the right instruction. So it's going to be written into memory. So whatever is in MDR at the end of the mem stage is going to be written to address 18 in memory. And at the end of the mem stage, the value in MDR doesn't change. It's still like the data, whatever was in R1. So the value for MDR, whatever is in R1. R1 was never changed here, or nothing was loaded into R1. So we look here, if not provided, has a value of 2. So R1 is 2, MDR is 2, because that was the last thing that was loaded into MD. Yeah. Oops. Where's one? Then D. Provide operation and operands for instruction 8. Oops. Okay. Instruction 8 is a load from memory. That's the operation, it's a load, since you're loading into this register from this address. The operands, there are 2. One of them is register R2 is the destination, since the arrow is pointing there. And the source is memory address 16. So you're right, like, I guess instruction is load. Destination, you said it was R2. Source, memory address 16. Alright, E. Provide the value for the PC at the end of the exec stage of instruction 7. Okay, instruction 7 is a branch instruction. Branch not equal. Branch not equal will test. Is R3 equal to 0? If it's not, then it's going to go to Y. If it is, it's just going to skip and go to the next instruction. Do nothing. Okay. Branch instructions, I think, yeah, they go fetch, decode, and then exec. You don't go to memory because we're not going to memory. There's no reason to go to memory. There's no write back. We're not writing anywhere. So there's fetch, there's decode, and what is it asking? It's asking at the end of the exec stage. At the end, what is the value of PC? Well, that depends. It depends if A was not equal to B, or in that case, was R3 equal to 0? First, we have to determine that. Let's see. R3, the last time it was changed is right here. R3 was R2 minus R2. So anything minus itself is 0. So yeah, it is 0. So R3 equals 0, and this only branches if R3 is not equal to 0. So it's not going to do anything. It's not going to go to Y. It's just going to go to the next instruction. So the value of PC at the end of the exec stage will just be whatever was last loaded into PC. So this doesn't happen, right? Because A is equal to B. In that case, R3 is equal to 0. This doesn't happen. And the last time PC was loaded to the address of the next instruction. So that's the last thing in PC. And that's going to be the answer. So it's going to be the memory address of instruction 8, which is 23. Yeah, 20. Okay. And total memory reference count for executing instructions. Okay. Total memory reference is like, well, all of them have one memory reference to get the instruction for the fetch stage. All of them go to the fetch stage, all of them go to the bus. So all of them have one, at least one each. Now for store and load, you have another bus reference. I mean, you go to memory again to write or to read from the address. This is a read. I mean, this is a write. This is a write. This is a read. So each of these.
Будешь спать сегодня?
No.
Еще не то?
No.
No.
That's it. Okay, so total memory reference count. 1 for this, 2 for this, 2 for this, 1 for this. Okay, let's write it down. 1 plus the second instruction has 2. 1 for the one during the mem stage, right? Or was it? Sorry, 1 during the exec stage, 1 during the mem stage. And then instruction 3 also has 2. Instruction 4 has 1. Instruction 5 has 2. Instruction 6 has 1. Instruction 7 is 1. Instruction 8 is 2. So that equals to 12. Yeah. All right, that's question 1. Now question 2 is asking to map this string into a cache size 3, and we're using direct mapping. Okay. Two 28193762132. Oh, whoops. 3 7 6 1 3. Okay. This is direct. Direct mapping, just you do the address mod the size of the cache. Size of the cache is 3. So the first one's a miss, it's not in the cache. 2 mod 3 is 2. Second one's a miss, it's not in the cache. 8 mod 3 is also 2. So it replaces this one. And then this is a miss. 1 mod 3 is 1. This is a miss. 9 mod 3 is 0. This is a miss. 3 mod 3 is 0. Replaces 9. This is a miss. 7 mod 3 is 1. 1. So it replaces 1. This is a miss. 3. 6 mod 3 is 0. Yeah. So it replaces 0. This is a miss. 2 mod 3 is 2. Goes here. This is a miss. 1 mod 3 is 1. This is a miss. 3 mod 3 is 0. Okay. Total memory time is the number of hits times the cache time. Cache time is 3ns plus the number of misses times the memory time plus the penalty time. And there are, all of them are misses, right? Yeah, they're all misses. Okay. There are 1, 2, 3, 4, 5, 10 misses. Okay, that's part 1. The last one is, 2A set associative cache of size 2 with least recently used replacement. I think he means size 4, right? Yeah, I think you mean size 4. With least recently used replacement initially empty. Okay. Same memory reference string. Okay. This time with LRU. Okay. Oh, and it's divided to 2 sets. First is a miss. Oh yeah, we gotta keep track. In each set we have a LRU bit. We keep track of it. And I'm gonna keep track of it by underlining. Okay. We have a miss. The set it's gonna go to is gonna be, since we have 2 sets, the first set is set 0. Two mod 2, because we have 2 sets, gonna go in set 0. And since it's a fully associative cache, we just use FIFO. I mean, first in to insert the element, like in order from 0, 1, 2, 3, etc. So 2 goes here, and it is the least recently used. This is a miss. 8 mod 2 is 0, so it goes in set 0. 2 is still the least recently used. This is a miss. 1 mod 2 is 1, so 1 goes in set 1. 1 goes here, and it's the least recently used in that set. And then this is a miss. This is still the least recently used. This is a miss, and now it's a collision miss, no longer a compulsory miss. So it's going to replace the least recently used in set 1, since 3 mod 2 is 1. It's going to replace the underlined one, so this one. And now 9 is the least recently used. 7's a miss. 7 replaces 9. And 3 is the least recently. 3 and 7. 3 comes before 7. 6 is a miss. Replaces 2 since it's even. And 8 is the least recently used. Because between 6 and 8, you track back. Okay, I have both of them. 8 comes before 6. This remains the same. 2's a miss. 2 replaces 8. 6 is the least recently used. This remains the same. 1 is a miss. 1 replaces 3. 7 is the least recently used. And 3 is a miss. Replaces 7. 1 is the least recently used. Let me just double check this. Yeah. 6, 2, 1. Oh, whoops. Oh. Did he? 2819376. Oh, there's no 3. Okay. There's no 3. Total hits 0. Total misses 9. That's it. That's test 1. Yeah. Okay, now test 2. This is test 2. Okay, it says it's loaded with offset 25, 16-bit architecture, meaning each word, each instruction, each address is just 2 bytes long. So we're gonna increment by 2s. That's a thing to be careful of. Not by 4s, not by 1s, but by 2s. Okay. The first instruction's address is 25. The second is 25 plus 2. The third is 27 plus 2. The fourth is 29 plus 2, etc. Okay. Yeah. And then provide the value for PC during the decode stage of instruction 5. Instruction 5 is R-type. PC during the decode stage. Alright, let me go back to my notes on R-type. Decode stage, nothing happens to the PC here. So the last time PC was changed was at the end of the fetch stage for that instruction. So it's just gonna point to the address of the next instruction. Gonna have that in it. And the address of the next instruction, which is instruction 6, is just 35. So the first one's 35. Let me just make sure I'm correct. Yeah, okay. Provide the value for the MAR at the end of the write back stage of instruction 6. Okay. Instruction 6. Oh, this is not a memory address. This is a immediate value, aka R type with an immediate value, or I type. All right. So this just doesn't have the mem stage, right? Let's see. It's like this, except this is just like a 5, and I believe there's no. Yeah, there's no exec, and I don't think there's a write back stage for this. But what is it asking? Oh, there is an write back stage. Okay. I guess in the write back stage, it's just gonna write 3 into register 5, and it's gonna happen after the decode stage. This is not gonna happen. Yeah, write back is just gonna write the value 3 into R1. Now they're asking the value of MAR. We didn't go to memory, so it was never loaded. It was never changed since the fetch instruction. And the last thing we put in MAR was the PC for this instruction. So that means it's going to contain the address of this instruction. And the address of instruction 6 is also is 35. Yeah. Provide the value for the MDR at the end of the exec stage of instruction 3. Okay. Instruction 3 is a store write to memory. And we need the value of the MDR at the end of the exec stage. I go to store. At the end of exec stage, it loaded MDR with the value of inside the register. Inside R2. So that's what's going to be an MDR. Whatever is in R2, and we loaded R2 last time we changed R2, we loaded it with 25. So the value of the MDR is going to be 25. Yep. Provide the value for the Z register at the end of the exec stage of instruction 4. Instruction 4 is R type, means it uses the ALU. Okay. The Z is the ALU output, it's whatever the ALU outputs. So what is the ALU output? It does R1 minus R2. That's what's going to be stored in Z. Let's see. The value of R1 was never given, so each register initially has a value of 4. Okay, R1 is 4 minus 25. It's going to be negative 21. And that's what's inside Z. Let's just check. Sorry, I was doing instruction 5. No, it says instruction 4. So R2 is 25. R3 loaded from 55, and it says each data memory location has a value of 5. So it loaded in 5 into R3. So R2 plus R3 is going to be 25 plus 5, which is 30. That's going to be the value in Z. Okay. Total memory reference count. Oh, they're looped. Okay. Total memory reference count. Let's see. Okay. If you notice, R5 gets loaded with 3. Then it's saying if R5 is not equal to 3, go back to Y. But R5 is going to be equal to 3. So it never branches back to Y. So this is not a loop. It just executes all of them and then stops. And now the total data memory reference is basically the memory reference count for the data, not for the instructions. Each time we fetch, that's a memory reference for the instruction, but we're looking for only data, which is only the store and load instructions during the exec stage, or the exec/mem. Okay. Basically, data memory reference wherever you see brackets. There's 1, 2. There's only 2. Did I skip one? Oh, I did I skipped part E. My bad. That's part F. Part E is 2 plus the 7 for fetching the instructions. 1, 2, 3, 4, 5, 6, 7. So 7 for the instructions, 2 for the data references, and the total is 9. And then data by itself is just 2. Yeah, 1 loan and 1 store. The memory reference string. Okay, memory reference string, you just look at your brackets and you just list them going from up downwards. So you have 55 first, 5 next, and then there's no more. 55, 5. Alright, that's it. And yeah, that's the string. Okay, this round just direct mapping of the string. Alright. And it's a size 3. Direct is you take the reference, you mod it by the size. Size is 3. And that's where it goes in the cache, if it's a miss. This is a miss. 1 mod 3 is 1, goes in 1, location 1. This is a miss. 2 mod 3 is 2, it goes in location 2. Miss. 3 mod 3 is 0, goes here. This is a hit. Nothing happens. This is a hit. This is a miss. 5 mod 3 is 2. Hit. Hit. Miss. 2 mod 3 is 2. Hit. This is a miss. 4 mod 3 is 1. This is a hit. This is a hit. This is a miss. 5 mod 3 is 2. And this is a miss. 2 mod 3 is also 2. Total memory time. Again, it's hits times the cache time. Cache times 3ns. Plus misses times the memory time plus penalty time. Memory is 33, penalty is 1. 33 ns plus 1 ns. We have 3, 4, 5, 6, 7, 8. 7 hits, 8 misses. I just leave it like that. Next is fully associative cache. That means first in, first come, first serve. Size 3 with optimal replacement. Optimal, you basically, when you want to replace something, your bit goes to like, I mean, whatever you replace is whatever's not going to be anywhere in the near future. So it's like the opposite of LRU. It's similar, you'll see. Alright, same memory stream. Please they ask for total hits. Yeah. Okay, when inserting in the cache, the same thing. First come, first serve. If you miss, goes in 0. There's a miss, it goes after it. There's a miss, it goes after that. This is a hit. This is a hit. This is a miss. Right, and we go to the right until we find all that's in our cache, 1, 2, and 3. And then we check which one comes last, and that's the one we replace. 3, 2, well, we never found 1, so it's never gonna come anyway, so 1 is replaced. 5, 2, 3. This is a hit. This is a miss. Again, between 5, 2, and 3, which one comes last? I found 2, I found 3, 5 is last. 5 is right here, 2 and 3 are right here. So 5 we replace. 3, wait. Sorry, 3 is a hit. My bad. 2 is a hit. 3 is a hit. 4 is a miss. Alright, now, between 5, 2, and 3, I found 3, I found 2, I found 5. 5 comes last, 2 and 3 come before it. So 5 is the one we replace. 4, 2, 3. This is a hit. This is a hit. This is a miss. So between 4, 2, and 3, 2 comes next. 4 and 3 never come. You can replace whichever one. And this is a hit. Number of hits we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 misses 6. That's it. Yep. And yep. Alright. Any questions? I guess that's where I'm gonna end it.
Yeah. I guess optimal was a lot more self-explanatory than I thought.
Yeah, it's like LRU, but like you just instead of looking back, you look forward.
Yeah.
And it's still the last one you replace. LRU you replace the last one as well.
For the first set of questions on each exam, the one where I asked you to like do the find specific valve, like an instruction after blah 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 stage. I think that just requires like more practice, but I think we got it down.
Yeah. You can always look at the. Did I stop? No, I didn't. You can always look at this. I'll send you this one.
Yeah, if you can send it in the chat, and
Yeah, there's a
maybe
quick
somebody
example.
can pin it. I don't know who the server owner is, but if he can pin it, that'll be like really good.
Yeah, sure. Yeah, I'll send it.
All right.
Alright, I'm gonna stop this stream now.